there. Let's talk inverse trig functions. This kind of ties in some college algebra stuff that we had done previously when you talked about inverse functions. Now we're going to look at inverse trig functions specifically. And you have to kind of remember that, let's go back and talk about functions in general. Recall that a graph can be a function, but only if it passes a vertical line test. And that for a function to have an inverse, then that function's going to have to pass a horizontal line test. So you look at a function, and if it will pass a vertical line test, it's a function. If it will pass a horizontal line test, then its inverse is also a function. Let's look at these graphs that we've been using. We're just going to talk sine, cosine, and tangent here. The problem with these graphs, if you look, let's start with the sine graph. See how this obviously would not pass a horizontal line test? It passes a nice vertical line test. That's good. It's a function, but it won't pass a horizontal line test. Same with cosine. Same with tangent. What we do then is we restrict our domain so that it will pass that test. In other words, we're just going to pick a part of the graph that would pass that. So there's two things we got to make sure. We're going to make sure that the part that we pick, so we got this nice wave, and we're just going to pick a piece of it and use only that piece. And that piece needs to pass a horizontal line test, but it also has to represent a full range of values. You have to look at all the possible sine values. You can't just pick out a little piece and say, oh, this will work right here, because that isn't a full range of values. For instance, for sine, it goes anywhere from a -1 clear up to a +1. So the piece that we pick, we want to make sure shows that full range. So usually what we do is we start at 0 and we start tracking this thing. And so far we're good, we're good, we're good. It's passing a horizontal line test. But right here I run into trouble. As I turn around, that's going to be the part where it no longer passes a horizontal line test. I could start at 0 and go up, but then as soon as I turn around, I have problems. So the farthest I can get to is pi/2. But the problem is that's not a full range of values because I only went from 0 up to 1. What I'm going to do is I'm going to back it up so I can get down to -1 also. The piece that I want to pick out is this piece right here. It has a nice full range from -1 to 1, and that piece would pass a horizontal line test. If you were to graph the inverse sine function on your calculator, you're going to see just this tiny little piece of a sine wave. Now I want to kind of tie that back to the unit circle. What we're going to be looking at then, and when we're doing inverses, we are only going to be able to use angle measures that go from a -pi/2 to a +pi/2. Every time, if you do it in your calculator, if you do it in your head, whatever, the angle that you get back will always be in that range. So let's look at where that falls on the unit circle. A -pi/2 is an angle that goes backwards. There's -pi/2. Anything here, all the way to a +pi/2, so anything up here. All angles, inverse, when you're doing inverse sine, all angles will come from those two quadrants. And that'll make more sense as we do some examples, but let's kind of get it written first. Now let's come over here and let's look at cosine. So I'm going to start at 0 degrees or 0 radians, and it starts here at 1, so that's the highest it can be. And if I start moving, it's okay, it's passing a horizontal line test. So far it's good, so far it's good, so far it's good. Until I turn around, now I'm going to have a problem because I'm going to try to pass a horizontal line test. I can't get past here. I can go from here to here. Well, you know what? That's okay, because that's a full range of values. I go from a 1 clear down to a -1, and I never broke my horizontal line test. For cosine, that's going to be the piece we want, just this little piece of wave here. And if we were to graph the inverse cosine function on our calculator, that's the only piece that would graph. Now let's compare that to a unit circle. Angle-wise, you're talking from a 0 all the way until you get to pi. On the unit circle, 0 all the way until you get to pi. All of the inverse cosine angles are going to come from these two quadrants then. Now let's try tangent. We have to pick out a piece of a tangent wave or tangent graph that's going to represent the full range. So if I start at 0 and I go up, that's good, that's good. But as soon as I hit the pi over 2 and I have to come down, well, that's good, that's good, that's good, that's good, that's good. And then once I hit here, now I'm going to be repeating from over here, and so it's going to break the horizontal line test. So I like this, and I like this. I just don't love that there's a break in the middle of it. So I think what I'm going to do is, rather than counting that part and that part, I'm just going to take this one full wave, because it's going to give me the full range of values. It's going to go from negative infinity all the way to positive infinity. And it's going to have a full range of values. It's never going to break the horizontal line test. Basically, I'm just picking out one wave of the tangent graph. Now let's come back to the unit circle. What quadrants are these particular angles going to fall? Well, it goes from negative pi over 2, past 0, all the way to pi over 2. That's going to look like sine. Here's negative pi over 2, all the way past 0 to pi over 2. So anything here when I'm doing inverse tangent. We kind of need to keep track of this. This is going to be important, that when I give you a particular inverse function, you know which angles you are allowed to use. Now the one thing you do have to be careful about is anytime you're choosing an angle from this quadrant, you have to represent that as a negative angle, because that's what we were representing. We were saying it was a negative pi over 2. You couldn't call it 330 or 7 pi over 4 or whatever. You can't use the positive angle that gets you here. It was the negative angle that we were looking at. The other thing, so this is kind of just some key things before we get started. The inverse function, when we're talking inverse sine, we sometimes write it like this. And this is what it looks like on your calculator. When you do second sine, it has this little -1 there. That's an inverse function. We also use the term arc sine. That means the same thing. I'm going to try to use these interchangeably so that you get used to seeing them and recognizing that's the same thing. It doesn't matter. And really when you see that, what you look at it as though when you find inverse sine x, you're looking for the angle whose sine is equal to x. Let's try some. First thing I want to do on our notes here is just, and I'm doing it mostly for me since I have this. I know you have your notes in front of you and you can look back, but anytime you do arc sine, you've got to be using these quadrants. Arc cosine is these two quadrants, and arc tangent is back to these two quadrants. And I just got a whole bunch of them to try. Now this is actually something that we've sort of already done. You're basically thinking through your unit circle backwards. Let me make a little note down here what I'm talking about. We've done this type of thing. It'll look like this. Sine theta equals √3/2. And I've asked you, well, what would theta have to be so that the sine of it is √3/2? And the thing is, well, sine is your y value. So it's going to be √3/2. That's your long leg. That's going to happen up here. So it could have been pi over 3. But it also happens over here as a 2 pi over 3. It could actually happen numerous times because I could have a coterminal angle that wraps all the way around back to that or to that. And I could do it again, or I could go negative. I have an infinite number of solutions for theta here. But by me restricting what quadrants it can come from, that's going to designate what theta really is going to have to be. It's going to limit that infinite number of solutions. Let's try some. Arc sine of -1/2. Remember, that means the angle whose sine is -1/2. Sine is my y value. I'm down my short leg. That's going to happen right here, and it's going to happen right here. But notice that arcsine has to come from this quadrant, not this one. I'm going to name this angle. And because it's in this quadrant, I have to think of it as I backed up to that spot. That's a negative pi/6. Let's keep going. Next one. The angle whose cosine is -1. When is cosine -1? Well, that's your x. So cosine would be -1 right here at pi. Inverse sine of √2/2. So the angle whose sine is √2/2. Sine is going to be √2/2 at 45s. It would happen here, and it would happen here. But I have to use this quadrant. It's going to be pi/4. Arctangent of -1. So the angle whose tangent is -1. I come over here. Tangent is 1 on your 45s, so it could be here or it could be here. Except on this one it's +1 and I want it to be a -1. I must have to use this angle here. And remember that if it's in this quadrant, I don't get to wrap around to that spot. I have to back up to that spot. It's got to be a negative angle. I'm going to back it up a pi/4. Inverse sine of 2. The angle whose sine is 2. Sine 2. Remember, what's the highest sine ever gets? You should be saying in your head, well, the biggest it ever is right here at 1. Sine can't be 2. That's not possible. Doesn't happen. So I might throw a weird one in just every once in a while to keep you on your toes. Okay, F. Okay, now this is weird. This one is a decimal. Well, it's not straight off my unit circle. So every once in a while, we'll throw you a problem that's not on your unit circle. And if it's not on your unit circle, then you're going to have to type it in your calculator. You're going to do arcsine. Remember, that's the same as inverse sine. You'll be hitting second sine. And I guess just to be consistent, we've been in radians, so let's just stick with our radian measurement. And I'm going to make sure that I'm in radian mode before I ever get started. And then I'm just going to do second sine. .2447. And I got a 0.247. 2. Now think of what that means. That's an angle measurement in radians, and we've talked a lot about this. Remember that clear over to, well, let me use my bullet thing. So clear over to here is about 3 radians because it's pi radians, so it's about 3. This would be about 1.5. So a 0.24 is pretty low down here. So I'm going to guess that my angle is somewhere there, which should also make sense then because my sine value was pretty low. Sine would be 1/2 at a 30-degree angle, and this is below 1/2, so it's a pretty tiny little angle. Just wanting you to make this to make sense in your head. You could also do that in degree mode if it helps you to visualize it. You would just switch your mode to degrees and then do second sine of 0.2447. And it's a 14.16 degree angle, so it's a very small angle. Okay, let's keep going. Back to G here with them. Back on my unit circle, the cosine is √3/2. You can see why it's important that you know your unit circle because, boy, these problems are going to take you forever if you're having to draw out the unit circle every single time to figure out what one problem is. That's why we've practiced that so much. because it just keeps coming back at us. All right, going to cosine. The cosine is your x. When are you over to the right, your long leg? That's going to happen right there at pi over 6. Can't do that one because that would be a negative. I want the positive, pi over 6. All right, next one is not a unit circle. So I'm going to stick with being in radians. Check to make sure you're back into radian mode. And then you're just going to hit second tangent, negative 8.45. And I get a negative 1.45. And that would be in radians. Oops, totally misspelled that. All right, these are for you. I want you to practice on this set. But I only want you to do the circled ones there. Some of those are repeat from what we just did. So just do these 3 problems right here on your own. Pause the video, make yourself think through it, and come up with those 3 answers. All right, check your answers. Make sure that they match what I have, and then we'll move on. We're going to do kind of some combined functions. So we really got to think through these. We're going to do 2 of them kind of in one problem. Looking at this, I'm going to just work inner to outer. The first thing I'm going to do is the inverse cosine and figure out what that angle would be. And then I have to come back and find the sine of that particular angle. The inverse cosine of root 3 over 2. You're looking at when is cosine root 3 over 2. That's when you are over a lot. So that would be your pi over 6. And now you're going to find the sine of pi over 6. It's always good to kind of envision where you're at because that doesn't change. I'm still at that same spot. And then the sine is a 1/2 at that because I'm only up a little bit, my short leg. Let's try F. Again, you're working on the inside first. Inverse cosine of a negative root 3 over 2. That's your x value. And it's going to be the long leg, so you're going to go way over here, negative. That angle is 5 pi over 6. And then you're looking to find the cosine of 5 pi over 6. Well, you're back where you started. You're at negative root 3 over 2. Let's do G together here. Inverse tangent. Okay, root 3 over 3. Trying to think, when is tangent root 3 over 3? That happens when you're close to the x-axis at all your pi over 6 stuff, but it's a positive. It didn't give me my fraction bar there, sorry. It's a positive root 3 over 3. That's going to keep me up in this quadrant. It's going to be this one right here. That angle measurement is pi over 6. I'm going to come back then and have to find the sine of pi over 6, which is 1/2. All right, why don't you try, well, let's do one more together, and then I'll turn you loose on some. Inverse cosine of 1. When is cosine 1? That happens, it's your x, it's when you're straight this way, it's just 0 degrees. And then you have to find the tangent of 0 degrees. Happens to be 0. Okay, I want to go the other way here. I'm going to actually find the sine of a particular angle, and then we'll come back and do the inverse of it. What is the sine of 5 pi? Notice on this one that you're kind of taking the sine and then you're coming back and doing the inverse sine. The last time we did that, it just took us back where we started. That is not always going to be the case. 5 pi is not within my acceptable range of answers for inverse sine. So you really got to think about what's going on. Here's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. All right, what is the sine of that value right there, of that angle? Well, you're up 0. So that whole thing is going to end up being 0. That means I get to come back then and find arcsine of 0. Well, 0 is back over here. Well, let me backtrack. I just found the sine value of that, and now I'm looking for the angle whose sine is 0, and that would happen right here because my sine value is 0. Not the angle 0, but the sine value is 0 there. I'm up nowhere, so 0 degrees or 0 radians. Let's try it again. See how you're doing the inverse of the same type of function? You would think those would just cancel and you would get this, except this is not in my acceptable range of values. Got to figure out where that's going to fall. 11 pi over 2. Here's 1/2 pi, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves, 9 halves, 10 halves, 11 halves. Okay, I'm basically straight down. What is the cosine on that one? And you should say 0. Then you're going to do the arc cosine of 0. What is the angle that has a cosine of 0? And this has to fall back into our acceptable range of, for cosine, the top 2 quadrants. So in the top 2 quadrants, when is cosine 0? That happens to be right here at pi over 2. All right, these two are yours. Oh, no, they're not. Sorry, these are different. I guess I didn't have as many practice ones in here as I thought. Okay, so let's try a couple of these. I'm doing them all for you. You don't have to do anything. How lucky is that? Notice on these that these are not unit circle questions. These are the type where you have to draw the picture. Okay, we can do this. Arc cosine is 2/3. Inverse cosine has to come from your top 2 quadrants. I'm going to draw a triangle. And since the cosine is going to end up positive, I know it's going to be in the first quadrant. I'm going to draw a triangle up here in the first quadrant. And whatever theta is right here, I know that the cosine of it is supposed to be 2/3. That's adjacent over hypotenuse. And then I can do Pythagorean theorem. It'd be 9 minus 4. This is the square root of 5 for that leg. I never really figure out what theta is. Previously, I'd always then write what that angle is. I still don't know what theta is without a calculator. But I don't really care because what I'm wanting to find out is what the tangent of that theta is. Once I've drawn the triangle out, now I'm just going to come back and say, well, what is the tangent of that particular angle? And looking at it, that's just going to be opposite over adjacent. Let's try another one. Arc sine is -3/5. Recall that for arc sine, you're going to be in these 2 quadrants over here. Since the sine value is going to be negative, that tells me I'm going to be down in this quadrant. I'm going to draw my triangle down here, put theta in there, and say the arc sine is going to be opposite over hypotenuse. Opposite is going to be the -3, hypotenuse is going to be 5, and doing Pythagorean theorem, 25 minus 9 is 16, square root, that's 4. Nice little Pythagorean triple there. Now, without ever really finding theta, I now have the triangle drawn so I could figure out what cosine theta is. And that's just going to be adjacent over hypotenuse. Last type of problem, which is kind of a preview for what is to come and why we're bothering to do these inverses, it all leads us to being able to solve equations. I've got a couple of them here. I started with a pretty basic one and then I gave you a monster. So let's start with the basic one. What you're trying to do is solve for theta. I need to start isolating this tangent theta and getting it by itself. So just using simple algebra techniques, I'm going to add 5 to the other side. I'm going to divide by 2. And I'm down to -1 equals tangent theta. And to get rid of the tangent, what we really do is we take the inverse tangent, we undo the tangent with an inverse tangent of both sides. Now what that looks like is inverse tangent of -1 is equal to, the tangents here cancel and I just get theta. Now I showed that nice this time. That's probably going to be the last time I do that. In the future, I'm just going to look at this right here and I'm going to say, oh, I'm looking for theta. What is the angle that would have a tangent equal to -1? And I don't really have to show all those steps. It's really the same thing. What is inverse tangent of -1? Inverse tangent of -1. When is tangent going to be -1? Okay. Tangent is 1 at the 45s. Oh, and I have to use these two quadrants. But it's a positive 1 here. It's a -1 down there. Remember that you don't get to call that 7 pi over 4. You have to call it the negative angle. It's going to be a negative pi over 4. We start off when we just do some basic algebra techniques, and then you're back to just doing that inverse function to figure out where you're at on the unit circle. This next one looks crazy hard, but they always will come out nice when they get crazy hard like this. Well, I mean, they don't have to, but they're gonna. Trying to get this theta by itself, so I'm going to try to isolate the sine theta. I'm going to move the 5, and then I'm going to get rid of the 2/5. Let's subtract 5 on both sides. That doesn't subtract very nicely. It's like, let me rewrite that so you see what's going on. It's really a -5 over 1 of those fractions. Cancels there. 2/5 sine theta is equal to 25. I'm going to get a common denominator of 5, so that's going to turn into 25. I'm going to have 25 plus the square root of 2 minus 25 all over my common denominator of 5. And look what happens to your 25s in the numerator. Those are going to drop off. And you really just have root 2 over 5. Now I'm going to multiply both sides by 5/2 to get rid of that fraction. I'm left with sine theta equals, remembering that the 25s dropped out, all I really have is this root 2 times this 5 and 2 times 5. And then the 5 and 10 can reduce, so sine theta is equal to, root 2 over 2. That's on my unit circle. How convenient. When is sine going to be root 2 over 2? So we're basically doing that inverse sine to figure that out. Inverse sine of root 2 over 2, theta would have to be pi over 4. You're basically just doing the unit circle backwards, and I'm throwing you all kinds of different types of problems to make you think through that. Hope you know that unit circle well. Good luck.